Hello students, welcome to the first lecture, online lecture of Statistical Modeling for Business Analytics. I am trying to record the lecture with some, I will have the slides in front of me, and there will also be some amount of board work which I will try to do with a paper. Because I am doing this for the first time, there may be some glitches with the board work or something. Um, I I hope you will be able to understand what I am saying in any case. Okay. So what is the topic we will start with today? We are going to talk about panel data. Okay. So this is the outline of the presentation. This is the outline of what we'll talk about. First, we will discuss what panel data is and why it is useful. Then we will talk about panel data with two time periods. And then we will talk about something called fixed effects regression, or also entity fixed effects regression. Then we will talk about regression with time fixed effects. And finally, we will talk about standard errors, and we will discuss a particular application. And as before, in this course, we will explain the whole idea of panel data using this particular application. So before we go any further, first we have to talk about what panel data is. So far, when we have been looking, the kind of data we have been looking at is called cross-sectional data. That is, we are looking at several entities or individuals at a given point of time. This kind of data is known as cross-sectional data. Now, you could also look at a single entity over different periods of time. Okay, so you could follow the same entity for different periods of time. So, for instance, you could look at how GDP of a particular country is growing over time, or how inflation is growing over time. And this kind of following a particular variable, looking at the values of the variable over time, is called time series data. So on the one hand, you have cross-sectional data, which is for a cross-section of entities at a given point of time. And on the other hand, you have time series data, which is looking at a given entity across different points of time. Now, panel data is combining both. So you are looking at a cross section of entities, and you are following that entire cross section of entities over different points of time. So, for instance, suppose the government does a census study. Okay, so it does a census study in 1 year. It goes to many households and asks them questions about different kinds of things, like what their income is, what their consumption is. All of these things it looks in 1 year, say 2001 or something. And then it goes back and asks the same households in another period of time, 2002, and another period of time, 2003. And then when it gathers all of this data together, this data for the same entities followed over a period of time is called panel data. Now, why why is using panel data useful, or why do econometricians follow panel data? That is something we will discuss in a little bit greater detail later on. Okay, so first we talk about we define we give a formal definition for what a panel data set is. A panel data set contains observations on multiple entities. Okay, these entities may be individuals, they may be states, they may be companies, they may be countries. Each of these entities, each entity is observed at two or more points in time. Okay, so even if you observe them over just 2 points of time, even that is called panel data. But if you have more number of years that you are observing the same entities, that is, of course, you have a larger panel data set. So what are some of the examples? You remember we talked about the California school districts, the 420 California school districts, where we looked at the class size and the performance of students in those classes. So that at a given point of time, what we looked at originally was the cross-sectional data, where we looked at this data across a cross-section of California school districts at a given point of time. Now, if you went back to those school districts and again measured once in 1999 and again in 2000, so now you have 420 multiplied by 2, that is, you have a total of 840 observations. Okay. Or for instance, you could have data on 50 US states. Each state is observed in 3 years for a total of 150. 50 multiplied by 3, 150 observations. Or you might have data, sometimes you might even have data on individuals. So for instance, if you are looking at, say, individuals who have some kind of a, who are being polled for their opinions, or who have some kind of disease, and you are following them, it's called a cohort study. Okay, so when you have a cohort of individuals, a specific set of individuals, and you keep going back to them and measuring some variables over time, then that would also be known as a panel data. So how do you write, what is the notation for panel data? Okay, so if you remember, when we looked at cross-sectional data, we wrote it as yi is equal to beta 0 plus beta 1 x1 I plus ui. So this is for the ith individual. You have data at a given point of time. Now, since you are measuring the same individual, you are measuring the variables for the same individual over time, you now add another subscript, that is yit is equal to beta 0 plus beta 1 x1 it plus uit. So now you have I and you have t, and you have here also you have I and t, and here also you have I and t. Okay, so the I index, the I subscript stands for the ith entity, and the t subscript stands for the tth time. And here we are assuming that there are n number of entities, so I goes from 1 to n, and t, which is a new dimension that we are including, t goes from 1 to capital T. So if you have one regressor, the data is written like this: xit and yit. Okay, so suppose you have k regressors. So you are not only including one variable to explain y, now you are going to multiple regressors. So you have x1it, x2it up to xkit. I goes from 1 to n and t goes from 1 to t. Okay, so it is important to realize that you are observing each entity at different points of time. Okay, panel data is also known as longitudinal data, and balanced panel indicates that you have data for each of the I entities for each period in time. Okay, so if you were to write it out, in fact we will look at that. So suppose you have okay, this we will talk about when we start discussing the example. Okay, so why are panel data useful? Why do we even look at the same entities at different points of time? So if you remember, one of our concerns when we used cross-sectional data, one of the things that we talked about was that you must try to include all the variables that if you did not include them, then there might be an omitted variable bias. So sometimes though you do not have data for those things, for those omitted variables. Many of you would have done your first project on multiple regression, and many times you said, well, this could be the omitted variable bias that we are missing out, and we don't know what to do about it because we don't have data. Okay, so sometimes panel data allows you to control for those variables, even though you do not have data for those directly, and you are not including them in your model, but you might be able to control for them. So what kind of omitted variables might you be able to control for? One kind of omitted variable is something that varies across entities but remains constant over time. Okay, so now let me give you an example. For example, we looked at the school districts, where you had different kinds of you had different school sizes, class sizes, and you had different class performances. Now, other aspects of the school district, which varies from one school district to another, maybe the number of schools that are there in a particular school district, or the kind of people, the average income of the residents of that school district. Now, these things may differ from one district to another, but may not change over time. If you remember, we said that the income of the parents of the children might have an effect on their performance in the classes. But uh, how do you even, you could try to include the average income, but you are not really interested in the causal effect of income on performance. All you want to do is you want to control for the effect that income might have. So you want to have a control variable. So if in absence of the control variable, you can just say, well, income differs from entity to entity, but over time, the relative levels of income across different school districts may remain the same. So when you want to control for these variables, panel data is useful. These variables may be unobserved or unmeasured. Okay, so the idea is that if the omitted variable does not change over time, then any changes in y over time cannot be caused by the omitted variable. So basically what we are saying is, you take stuff that doesn't change. See, basically you are looking at what effect a change over time of, say, class sizes has over change in performance in class sizes. And there are some other stuff that remains constant over time, and you just control for those variables, and you just look at only things that change over time. There was a bit of a pause over there because the camera stopped working for one of the parts. We are going to start again. We take a particular example of a panel data set, and in this case we are considering the effect of alcohol taxes on traffic deaths. So the idea is basically that if you want to reduce traffic fatalities, one cause of traffic fatalities may be due to drunk driving. If you want to reduce the number of people who are drinking and driving, you may want to increase the prices of alcohol. And so if you impose taxes on alcohol, people may be less, they may buy less alcohol, they may drink less, and they may drink and drive less, as a result of which traffic fatalities may be less. So if the government is sort of trying to look at different policy measures, one of the policy measures they can consider is increasing alcohol taxes. So what do we do in order to see whether there is in fact a causal relationship between alcohol taxes and traffic deaths? What we look at is, we look at data from 48 US states, that is, the number of entities is 48, and we look at two variables from these 48 US states over 7 years. So we have data for 1982, 1988, 1982, 1983, so on and so forth, up to 1988. So this is what the data looks like. So basically we have, say, different columns for the different variables that we might include. Right now we have only two variables that we are looking at. So the first column is for the entity. The second column is for the time period. This column is for the y variable and this column is for the x variable. Entity is denoted by I and time period is denoted by t. Each dependent variable is for the ith entity and the tth time, and the independent variable is also for the ith entity and tth time. So we have, say, suppose the first state we look at is California. We have California data for 1982. Then we have, say, another state which is, say, Arizona. We have data for that for 1982. Then say we have another state which is Texas, and we have data for that also for 1982. Like this, we have data for all the states, say Florida 1982. So if you were to look at just 1982 data, this is the familiar cross-sectional data that we know. Okay, but suppose you also have data for each of these states for another year, that is 1983. So this is two time periods. So for each of the states, you have data for 1983, you have data for Arizona for 1983, you have data for Texas for 1983, and so on and so forth until you have data for Florida for 1983. Like this, you have data for till 1988. So now basically, if you when you have just 1 year's data, you call that cross-sectional data. When you have many years data, you call that time series data. Okay, so again you have California 1988 and so on and so forth. So what is the total number of data points that you have? You have 7 periods and 48 entities. So you have 336 data points. What is the y variable over here? This is traffic fatality rate. That is the dependent variable that you are interested in. And this is x is alcohol taxes. Alcohol taxes. Both traffic fatality rate and alcohol taxes may vary across entities and also for the same entity over time. So 1982 traffic fatality rate for California may be something, 1983 traffic fatality rate for California may be something else, and 1988 traffic fatality rate for California may be something else. So you may have something like 3% traffic fatality rate, here you may have 2.8%, and here you may have 2.2%, and so on. And alcohol taxes may be 1.4%, and here you may have 1.6%, and here you may have 1.8% alcohol taxes. So it is varying over time and it may vary across entities. So Arizona may have, for instance, 2.2% traffic fatality rate, and so on and so forth. Okay, so you may have other independent variables such as x2, this was x1, this is x2 it, this is x3 it, and this would basically be this might be legal driving age. Of course, the point is that legal driving age may not be something that changes over time. Legal driving age, drunk driving laws, this may change or not change. What might be some of the drunk driving laws? So for instance, in some states, if you drink and drive, your driver's license may be suspended. Some other states, if you drink and drive and cause an accident and as a result someone dies, you may be sent to jail because of manslaughter, So the severity of the punishment that you might get if you drink and drive, these laws may change from state to state. So these might be the other variables that you are looking at. Now, if you were to just take the traffic fatality rate and the alcohol taxes and take all of the data together without sort of giving taking into account the fact that you have the same entity measured over different years, you don't take into account that particular specific detail, but you just take them all as if it is a cross sectional data, and you plot fatality rate on the y-axis and beer tax on the x-axis. So as you can see, the beer tax goes from around $0 per case to around $3 per case, and fatality rate goes from around 0 fatalities per 10,000 to around 4.5 fatalities or 4.25 fatalities per 10,000. Okay, but if you were to just plot the data like this, as if this is called pooled data. Okay, so if you were to plot the data like this, you find that the fatality rate is related to the beer tax, but the coefficient is positive. So basically what you are finding is that the coefficient is 0.15. So what is going on here? As the alcohol taxes goes up, there are more traffic deaths. Does this sound reasonable to you? Possibly not, right? So we will look at it a little bit more. So why might there be higher or more traffic deaths in states that have higher alcohol taxes? So there may be other factors that determine traffic fatality rate. So one may be the quality of automobiles that people are driving in that particular state. So some state that has higher income per capita, those individuals may be able to afford higher, better quality automobiles. So both the person who is driving the car that caused the accident and the car in which the person who had an accident or who was hit by another car, both those cars, if they are of higher quality, then possibly no one may die. The airbag may deploy, or the body of the car may be stronger or something. It may not be a very old car, the car that is driving, the driver's car, that may not skid or something like that. So as the quality of automobiles increases, which is possibly dependent on the per capita GDP of that particular state, as the quality increases, the number of fatalities may go down. Quality of roads. Now, obviously, as the quality of roads increases and the roads are maintained better and the visibility is higher, there are better markings on the road. So then also you expect that these will help drivers be more careful. It will help drivers be able to drive better. They will not lose control of their car, and they will be able to see oncoming traffic, as a result of which so many accidents may not be caused, and because of this the fatalities may be less. But see, this has nothing to do with drunk driving. This is uh, an independent variable, which is probably a function of which is probably a characteristic of the state that we are talking about. Another thing might be the culture around drinking and driving. So a particular state may have a bit of a lax culture where people party a lot. Drinking and driving is not considered to be a very bad thing socially. People tend to do that. So you may have some states, I mean, if I say such things, I don't know whether it is completely true or not, but some of the states like Florida, where young people may go to party, over there it may be that there is a culture around drinking and driving which may lead to greater fatalities. I'm not particularly fully sure of this, but I'm just throwing it out as a possible idea. Another thing, of course, that will affect fatalities would be the density of cars on the road. As the density of cars increases, the probability of accidents increases, and the probability of fatal accidents also would increase. Okay, so all of these are extraneous factors that might affect the fatality rates. Remember that when we are looking at fatality rates, the we only have access to data about fatality rates. We do not have access to data about the cause of the accident, which caused that particular accident, which led to the fatality. So if we had directly, drunk driving caused accidents, then that would make our job a lot simpler. But what we do not have access to such data at such great detail. We do have access to data at a more aggregated level, which is basically the traffic fatality rates. So, these omitted factors that we just talked about, that was the traffic density, the culture around drinking and driving, quality of automobiles, quality of the road, these factors could cause omitted variable bias. So, let us take one particular example. Now, if you remember from our early lectures, what are the conditions for an omitted variable bias to happen? Um, for the omitted variable, suppose your variable of interest is x1. Okay, so suppose your variable of interest is x1, plus yi equals to beta 0 plus beta 1 xi plus ui. Okay, you have included x1 and you are trying to see the effect of x1 on y, x1 on y. You have omitted some variables which are x2, x3, and so on and so forth, x4. For x2 to be an omitted variable, x2 should be a causal factor for xy, causal factor for y. It should have causation for y, and x2 should be correlated with x1, right? So these are the two conditions for x1 and x2, for x2 to be an omitted variable. Now let us look at high traffic density. High traffic density means more traffic deaths. So this is your y variable, traffic deaths. So high traffic density has a causal factor for it, is a causal relationship towards y. Also, certain states that have lower traffic density tend to have lower alcohol taxes. So, in this particular case, the western states which have lower traffic density also have lower alcohol taxes. So, x2 happens to be correlated with x1 also. Even though there isn't a particular causal relationship that we are finding over there. The two conditions for omitted variable bias are satisfied. Specifically, high taxes could reflect high traffic density, so the OLS coefficient would be biased positively. That is, high taxes, more deaths. If we leave out high traffic density as one of the omitted variables. So what should we have done if we were not looking at panel data? We would have included this variable. So we would have said beta 0 plus beta 1 x1i plus beta 2 x2i plus ui, where x2 is now traffic density. Okay. And x1 is beer taxes. And yi is fatality. So like this, we could include all of these other variables that we talked about. But it's suppose you don't have data for traffic density, or you don't have data for culture, or you don't have data for the quality of roads. So what you do is you introduce the idea that you could use a proxy variable, that is z, which is a proxy variable, which is an indicator variable for each entity. Proxy variable, indicator for each entity I. Okay, so now each entity I, each state in the United States differs from each other in certain ways, and these differences don't change over time. So traffic density in certain states may be always high compared to certain other states. There may be small changes, but overall the traffic density, the average traffic density in a particular state may not change much over time. Similarly, the culture about drinking and driving may not change over time. So you take all these factors and you say each state has a certain characteristic which leads to people there being a greater chance of people drinking and driving, or there may be a greater chance of fatalities which are specific to that particular state. So you include that as a proxy variable. So panel data lets us eliminate, when you include such a thing as a proxy variable, all of these variables are included, and it allows you to avoid omitted variable bias. Similarly, the second example is of cultural attitudes towards drinking and driving. Again, cultural attitudes are a determinant of traffic deaths. So X3 is a determinant of Y, and X3 is probably associated with X1, that is where people are more lax about drinking and driving. In those states, maybe the beer tax is also lower. So the two conditions are satisfied. So high taxes could pick up the effect of cultural attitudes towards drinking. So if you don't include this variable, you will have the beta 1 for the taxes will be biased. Okay, again, panel data, as we said, if you include a proxy variable, then it will include the effect of the cultural attitudes, and it will let you avoid omitted variable bias.